something really fundamental about our universe. It goes way beyond maybe what you learned in basic science class. We're talking particle spin. But look, we're not just sticking to the familiar spin 1/2, electrons and things.
No, definitely not.
We're diving deep into particles with higher spins. And we're kind of guided here by insights from the article, Higher Spin Particles in the Quantum World.
That's right. And when we talk about a particle's spin, it's a core quantum mechanical property. It's like an intrinsic angular momentum.
Okay, but not like a spinning top.
Exactly. Not like a spinning top or a basketball. It's inherent, and crucially, it's quantized.
Quantized meaning it only comes in specific amounts.
Precisely. Think like energy levels in an atom, Spin can only have these discrete values, either whole numbers 0, 1, 2, or these half-integer values, like 1/2, 3/2, 5-halves.
And these values, they're like labels.
They really are. They act like fundamental labels for the particles, telling us a lot about them.
Okay, so these spin values, these labels, they tell us something really important about how these tiny pieces of reality behave.
Absolutely. They're so significant, actually, that they broadly divide all particles into two big groups, fermions and bosons.
Right. Fermions, those are the half-integer ones.
Yep. The half-integer spins 1/2, 3/2, and so on. These are basically the building blocks of matter as we know it. Think electrons, quarks inside protons.
And they follow a special rule.
They do. The Pauli exclusion principle, which is, well, surprisingly important for why matter is stable, why you don't just fall through your chair.
Huh. Okay. Good rule to have.
Definitely. It basically says no two identical fermions can be in the exact same quantum state at the same time. They need their personal space, you could say.
Like quantum introverts. Got it. And the other category, the bosons.
The bosons have the integer spins 0, 1, 2, and so on. They're much more social. Multiple identical bosons are perfectly happy occupying the same quantum state.
Oh.
And what's really key here, especially for today, is that the particles carrying the fundamental forces, they tend to be bosons.
Which brings us right to the core of our deep dive today. These particles with spins greater than 1/2. The article makes it pretty clear understanding these is, well, critical.
It really is. For getting a handle on the fundamental forces, the constituents of the universe, it's like moving beyond just the alphabet of reality to understanding the grammar.
Yeah, I like that, the grammar of reality.
So think of this as maybe a shortcut to a more advanced part of quantum physics, but hopefully a revealing one. We'll try to highlight some surprising things and, explain it closely without drowning you in jargon.
Okay, sounds good.
Yeah.
So where does our exploration of these higher spins begin? The article starts with spin 1 particles. Vector bosons, they're called.
That's right. Spin 1 particles, these vector bosons, are basically the force carriers we just mentioned.
Okay.
They have that integer spin value, S1, which means their spin can point in 3 possible ways in quantum space. We call those projections: -1, 0, and +1.
3 options.
And being bosons, no Pauli exclusion, they can pile up. What's really remarkable is their direct link to the fundamental forces through what physicists call vector fields.
Vector fields.
Well,
like the influence.
kind of. Think of the field as the underlying influence, and the spin 1 particles are the little packets, the quanta, that transmit that influence. The messengers.
So these are the particles actively making things happen?
Yeah.
The messengers running around orchestrating the universe's interactions. Give us some examples. Who are the key players in this spin 1 group?
Okay, absolutely. First up, the photon, symbol gamma. It's the quantum of the electromagnetic field.
Light, basically.
Light, radio waves, X-rays, but also the force holding atoms together. It's massless. Spin 1 carries the electromagnetic force. Pretty fundamental.
Okay, what else?
Then you have the W and Z bosons.
All right.
W plus, AW and Z0. Now, these are different. They're massive.
Wait, massive force carrier?
Yeah, it's a bit counterintuitive, isn't it? Their discovery was this huge triumph for the standard model of particle physics. They carried the weak nuclear force.
The weak force that's involved in radioactivity.
Exactly. Things like beta decay.
Okay.
So, massive particles carrying a fundamental force. Still kind of amazing.
It really is. That does challenge the everyday intuition. Okay, who else is in the spin 1 club?
Well, then we have gluons, little g. These are the mediators of the strong nuclear force.
The force holding atomic nuclei together.
Holding the quarks inside protons and neutrons together specifically. Now, gluons have this property called color charge. Nothing to do with visible color, it's just a name.
Like electric charge, but for the strong force.
Sort of, yeah. It's the interaction of this color charge that binds quarks. There are actually 8 different types of gluons carrying different combinations of this color charge.
8 types. Wow.
And importantly, like quarks, gluons are confined inside particles called hadrons, protons, and neutrons or hadrons. We don't just see free gluons flying around.
Okay, they're stuck inside.
Pretty much. And finally, in the spin-1 category, you also have things called vector mesons, like the rho, omega, phi particles.
Are these fundamental?
No, good question. They're composites, made of a quark and an antiquark bound together. Their combined spin, plus maybe some orbital motion inside, adds up to a total spin of 1.
Gotcha. So spin 1 is really dominated by these fundamental force carriers, plus some composite relatives. Okay. The article then moves on. Spin-Three-Halves, now we're back to half-integer spins. Fermions again.
Exactly. Spin-Three-Halves means S equals 32, back in Fermion territory. So they do obey the Pauli exclusion principle.
Even these more exotic ones need their space.
They do. And their spin can point in 4 possible directions now. Negative 32, negative 12, plus 12, and plus 32.
More options.
Yep. And mathematically describing them gets a bit more involved. We use something called the Rarita-Schwinger equation, which is sort of a step up in complexity from the Dirac equation used for spin 1/2 particles like electrons.
Okay, so the math gets tougher. What kind of particles actually are spin-3-halves? They sound less common.
Well, one really prominent example is the delta baryons. Remember, protons and neutrons are baryons made of 3 quarks. Delta baryons are also made of 3 quarks, but the quark spins are aligned differently, so the whole thing adds up to spin 3/2. You get different types like Lu, plus N, and plus 0, dear, depending on the up and down quarks inside.
So they're like cousins of protons and neutrons?
Yeah, like heavier, more energetic, unstable cousins. They decay really quickly, usually into a proton or neutron and another particle called a pion.
Ah, fleeting existence then.
Very fleeting. Another cool example is certain omega baryons, particularly the omega minus. It's made of 3 strange quarks, and it also has spin 3/2.
3 strange quarks.
Yep. And its discovery was actually a huge deal. It confirmed predictions from the quark model before it was found experimentally. A real textbook case of theory predicting reality.
That is fantastic. Theory leading experiment. Now, the article also mentions a hypothetical particle here. The gravitino.
Ah, yes, the gravitino, symbol G with a tilde D.
B.
This one's predicted by theories that go beyond our current standard model, specifically supersymmetry, or AUY.
Supersymmetry. Is the idea that every particle has a partner.
Basically, yeah. LEUY proposes this symmetry between fermions and bosons. Every known particle would have a superpartner with a spin differing by 1/2. The gravitino is predicted to be the superpartner of the gravity particle we'll get to, and so it would have spin 3/2.
But purely theoretical for now.
Purely theoretical. Hasn't been observed. It really highlights how much we still might not know about the fundamental particle zoo.
Right. Lots of question marks remain. Okay, let's keep climbing the spin ladder. The article then talks about particles with spin higher than 3/2. What's up there?
Yeah, this is where things get even more interesting and honestly more speculative in some ways. We start talking about spin 2 bosons, spin 5-halves fermions, maybe even higher.
And potentially more theoretical challenges.
Definitely. The theoretical framework gets trickier as spin increases.
Okay, let's start with spin 2. Tensor bosons, is that the term?
That's the one. Spin 2 particles have spin quantum number S2. They're bosons, so no Pauli exclusion. And their spin can have 5 possible projections. Manic 2, manic 1, 0, +1, +2.
5 states.
Yep. And theoretically, massless spin 2 fields are deeply connected to something called the stress energy tensor.
Which describes energy and momentum.
Essentially, yeah. How mass, energy, and momentum are distributed and move through space-time. It's the source of gravity in Einstein's theory, actually.
Ah, okay. Which leads us to the big one, right? The graviton.
Exactly. The graviton, symbol G, is the hypothetical quantum of gravity. If it exists, it's expected to be massless and have spin 2.
The particle that carries the gravitational force.
Precisely. The messenger particle for gravity in a quantum theory. But detecting one. Ooh, boy. Incredibly difficult because gravity is just so incredibly weak compared to the other forces.
Like finding a needle in a cosmic haystack.
Maybe harder.
Yeah.
But what's fascinating is that string theory, one of the big frameworks trying to unite gravity with quantum mechanics, naturally predicts a massless spin 2 particle.
So string theory needs something like the graviton.
It basically pops right out of the math with the right properties, which is pretty compelling evidence for theorists, even though we haven't seen it directly.
Interesting. Are there any spin-2 particles we have actually observed?
Yes, but again, they're composites. We have things called tensile mesons. Examples are the F2-1270 and A2-1320. The names aren't too catchy, I know.
Particle physics naming conventions.
Yeah. Anyway, just like the spin-1 vector mesons, these are made of a quark and an antiquark. But here, the combination of their spins and their orbital angular momentum, like how they're orbiting each other inside the meson, adds up to a total spin of 2.
Okay, so the internal motion contributes significantly there. Right, now let's jump to spin 5-halves. Back to fermions.
Back to fermions, yeah. S equals 52. Half integer spin, which means 6 possible spin projections this time.
6 states. Do we know of any fundamental particles with spin 5-halves?
Not currently, no, but they do show up again in the world of composite particles, specifically as excited states of baryons.
Like those delta baryons we talked about.
Exactly. Higher energy versions of delta baryons, or even excited states of protons and neutrons themselves, sometimes called nucleon resonances.
So you pump energy into a proton, and it can become a spin 5-halves particle for a moment.
Sort of, yes. In these higher energy states, the quarks inside can have more complex configurations, their spins can align differently, and can have orbital angular momentum relative to each other. The combination can push the total spin of the whole baryon up to 5-halves.
So it's the internal dynamics again.
Absolutely. The particle data group, which is like the official catalog of particles, lists several of these excited baryon states with spin 5-halves.
Okay, and any purely theoretical spin 5-halves particles?
Well, some theories beyond the standard model might include fundamental spin 5-halves particles, but again, that's purely speculative right now. No discoveries.
So it seems like a pattern emerges. As we go higher in spin, we're often looking at these excited composite states. What about even higher spins? Spin 3, spin 7-halves.
Yes, exactly that pattern. When you get to spins higher than, say, 5-halves, you're almost entirely talking about composite particles or deep theoretical territory.
Let's touch on spin 3. That would be a boson, right?
Integer spins, so yes, a boson. And we actually do see some evidence for composite particles with spin 3, usually very short-lived things called resonances, popping up in high-energy collisions.
Like at the LHC.
Exactly. Experiments like LHCb have reported findings consistent with highly excited hadron states that behave like spin 3 particles. Again, it's the quark spins and orbital motion combining in just the right way.
Okay. And theoretically, is it hard to make a fundamental spin 3 particle work?
Oh, yeah. It gets significantly harder to build consistent, interacting quantum field theories for elementary particles with spin greater than 2. All sorts of technical problems can pop up.
Like what kind of problem?
Issues with maintaining fundamental principles like Lorentz invariance, the idea that physics looks the same for everyone moving steadily. For massless, high-spin particles, you run into trouble with gauge symmetry, which is tied to forces. For massive ones, you can get problems with causality effects happening before causes or unitarity, which basically ensures probabilities add up correctly. It's messy.
Sounds like a theorist's nightmare.
It can be. But it's also intriguing because these higher spin fields do appear naturally in frameworks like string theory and something called the AD-SCFT correspondence, which links gravity theories and quantum field theories.
So even though they're difficult to handle, theory suggests they might be important.
Exactly. It hints that maybe they're crucial for a deeper, more complete picture of physics, perhaps at very high energies or related to quantum gravity.
And what about even higher fermion spins, like 7-halves?
Same story, really. Composite baryons, especially excited delta states, can reach spins like 7-halves, even 11-halves in some cases. It's almost entirely down to the quarks having lots of orbital angular momentum inside.
So the higher you go, the more it seems to be about complex internal structure rather than fundamental point particles.
For observed particles, that definitely seems to be the trend. Fundamental particles with very high spin are, for now, mostly confined to theoretical exploration, facing these significant hurdles we mentioned.
But that exploration is ongoing.
Absolutely. This whole area of higher spin theories is a very active field of research. Physicists are pushing the boundaries, trying to figure out if fundamental particles with spin 2 can exist in a consistent way, how they'd interact, what role they might play. The hints from string theory keep people motivated.
Okay, so let's try to wrap this up. We've journeyed through this world of higher particle spins, Quite a diverse zoo.
It really is.
We saw the spin-1 vector bosons carrying forces, the hypothetical spin-2 graviton for gravity, spin-3-halves baryons like the delta, spin-2 composite mesons.
And then this increasing landscape of excited composite states as you climb higher and higher up the spin ladder.
It definitely feels like studying these particles pushes the very boundaries of our understanding, doesn't it?
No doubt. It forces us to confront the limits of our current theories of fundamental forces and the basic building blocks of everything.
Okay, that was a fantastic deep dive. If you had to boil it down, what's the single most important thing for our listeners to take away from all this?
I think the crucial point is that particle spin isn't just about spin 1/2. It's a fundamental quantum property with this whole rich spectrum of possible values.
And that value really matters.
It profoundly dictates how a particle behaves, how it interacts, whether it builds matter or carries forces. It's woven into the very fabric of reality at the most fundamental level.
So when you think about everyday forces like gravity holding you down or light letting you see, you realize it's all connected back to these, well, seemingly abstract ideas about particle spin.
Precisely. It underpins everything. And, it makes you wonder.
Go on.
Well, could exploring even higher spin particles unlock deeper secrets? Could they point towards new forces we don't know about? Maybe even new dimensions?
What would a universe dominated by very high spin particles look like?
Right. It's a really provocative thought, and it's exactly those kinds of questions that keep physicists digging deeper into these fascinating fundamental properties of our universe.